All right, so you very well know that IB likes us to work between different forms. In the last video, we learned how to write the vector equation of a plane. So in this video, we're going to talk about how to go from a vector equation to the Cartesian equation. All right, so the first thing we're going to do, we've got a plane. It contains these vectors, has this starting point, includes that point. So therefore, I'm going to create a vector equation first, essentially a vector equation. So I'm going to have R, which is going to be the plane, right? So the plane is going to be described, all the vectors, all the points within this plane by doing the A plus, and then here it just needs to be a parameter times B, and then plus a new parameter times C. Now you can use whatever parameters you want. I've chosen to use alpha and beta here. Lots of textbooks and actually the IB exam use lambda and mu. I chose these just because I want to be problematic and I don't want to do what everybody else does. But the parameters are unimportant as long as these two are different to show that you can do B and C different amounts of times. Okay, so the starting point is going to be that point that I know exists in my plane, 1, 2, 0. And then from there, I'm going to do alpha of vector 2, 1, 1. And I'm going to do beta of vector 3, 0, negative 1. Now at this point, I need to put it into Cartesian form. When we did this with lines, the easiest thing to do was to put it into parametric form, solve for the parameter, and then set the things equal to each other to get rid of the parameters. So we're going to follow a similar process here, recognizing that I now just have two parameters. So I'm going to go ahead and I'm going to write my parametric equations, which is going to be that x equals 1 plus 2 alpha plus 3 beta. I'm going to do y equals 2 plus alpha, and then I don't need the beta because it's beta times 0, right? So that's the middle line. And then I've got z equals 0 plus alpha plus negative 1 beta, so minus beta. All right, so at this point, I now need to use the three equations to solve for alpha and beta. Okay. You'll notice here that I can just say alpha equals y minus 2, and that's nice and wonderful. I'll be able to put that in for alpha. Here, I'm going to just do this where I'm going to say that beta is equal to alpha minus z, or z, depending on where you're from. And because at this point I can now put alpha in for alpha, and so I can say that beta is equal to y minus 2 minus z. All right. Funny story, my daughter, when she was growing up, we always said z in our house, but she had a teacher from South Africa, and this teacher from South Africa always called it zed. And so when she was singing the alphabet song, she'd do fine, wonderfully, until she got to Z, and then she'd be like, W, X, Y, and Z, and she wasn't quite sure how to finish the song because she wasn't sure if it was Z or Z. Anyway, not important to this process, but funny story anyway for those that know my daughter. For those that don't, too bad. Okay, so now I'm going to actually take these and I'm going to put them into my first equation here. Okay, so I'm going to say that x is equal to 1 plus 2 times alpha, which was y minus 2, and then plus 3 times beta, which was y minus 2 minus z. So at this point, I can solve and create a Cartesian equation. So just for the record, let's see what happens. So I'm going to have x equals 1 plus 2y minus 4 plus 3y minus 6 minus 3z. Normally with this type of equation, what we'll do is we'll put all the variables on one side and the constants on the other side. And so I'm going to write my final equation here. I've got x there. I'm going to have a plus 2y and a plus 3y, which I'm going to move to the other side. So that'll be minus 5y. And then I've got a minus 3z, which I'm going to move to the other side. So that's going to be plus 3z. And that will be equal to the 1 and the negative 4 and the negative 6, which are all still here, giving me a negative 9. And this is the Cartesian equation for a plane. All right? Very good. That's it for this video.